Welcome to the deep dive. Today we're diving straight into the technical core of electroencephalography EEG signal processing. Our mission.
That prompt seemed to work. It's actually did like a different intro, doing a different intro. So
Mission to pull out the most critical technical details and maybe some surprising facts for you about how raw brain signals get turned into, well, real understanding.
Yeah, and what's really key here is EEG's specific edge. It's non-invasive, pretty cost-effective, and captures brain electricity with incredibly high time resolution.
Ultra high time resolution. Why is that so critical?
Well, it means we see brain activity almost the instant it happens. That's a huge difference compared to something like fMRI, which can be quite slow, maybe only 2 frames a second.
Okay, so fMRI misses the quick stuff.
Exactly. So EEG is perfect for tracking fast mental processes or even some brain disorders where the blood flow changes fMRI looks for just aren't the main story.
So we're listening to these super fast, faint electrical whispers. How do we even begin to process that raw data into something meaningful? What are the essential first steps?
Right, so these EEG signals, they're direct signatures of what your neurons are doing. We capture them with electrode setups, could be on the scalp, on the brain surface, or even deeper inside. And then straight away, they get digitized. The core processing happens in, let's say, 3 main ways. Time domain, how signals change over time. Frequency domain, using things like Fourier transforms to see rhythms.
Like brain waves, alpha, beta, that kind of thing.
Precisely. And then spatial domain. Figuring out where in the brain the activity is happening.
Got it. And underpinning all that analysis, there must be some serious math, right, to model the brain's language.
Oh, absolutely. Models like Hodgkin-Huxley or the Morris-Lecar model are foundational. They describe the action potentials the electrical spikes neurons use.
So the model tells us why certain firings create certain EEG patterns.
Exactly. It helps us connect the dots from single neuron behavior to the network oscillations we actually measure with the EEG electrodes.
Okay, so we captured the signals, we have models for the underlying activity, but the brain's noisy, the environment's noisy. How do we zero in on the actual information we want?
That's where some really powerful algorithms come into play. Things like blind source separation, or BSS, and especially independent component analysis, ICA.
ICA sounds complex. What's the idea?
Imagine trying to pick out one voice in a really noisy room. ICA algorithms like Infomax or Fast ICA are designed to mathematically separate out different independent signal sources mixed together in the EEG recording. They're great at finding those unique brain signals, which often have shapes that aren't simple bell curves, what we call non-Gaussian. And they can pull out spiky artifacts like noise from an fMRI machine if you're doing simultaneous recording.
Okay, so that cleans things up. What else is in the toolbox?
Another really useful one is the Wavelet Transform, or DWT. It's fantastic because it lets you look at both time and frequency information together.
Like getting the rhythm and the melody at once.
Right. Kind of, yeah. It decomposes the signal into different components, giving you a richer picture than just looking at frequency or time alone.
Okay, powerful tools for dissecting the signal. But EEG data can look pretty chaotic, right? How do we make sense of that complexity?
That's a great point. We often treat EEG signals as chaotic systems. So we use tools from chaos theory dynamical analysis, things like Lyapunov exponents or fractal dimension measures.
Fractal dimension, like Katz, Higuchi.
Exactly those. They help us put a number on the complexity or roughness of the signal. Then, to actually sort these complex patterns, we use classification algorithms. Support vector machines, SVMs, are really common. They're good at finding the best boundary to separate different types of brain activity or states.
Like telling apart different mental states?
Potentially, yes. Or classifying seizure versus non-seizure data. And for grouping similar patterns without predefined labels, K-Means clustering is often used.
And what about how different brain areas talk to each other?
For that, we can use something called the directed transfer function, or DTF. It's like an advanced version of Granger causality, basically telling us the direction of influence between brain regions, even if their activity patterns overlap a lot.
Wow. Okay, so these aren't just abstract algorithms. Where are they making a real difference right now?
Oh, the applications are really transformative. Take epilepsy. EEG is standard, but new frameworks using deep learning like 1D CNNs by LSTMs on EEG data, they're achieving really high seizure detection accuracy, sometimes over 96%, even with just a few channels. That's huge for patients.
Better, faster diagnosis.
Definitely. And brain-computer interfaces, BCIs. Advanced signal processing is what makes them work, allowing people to control devices using thought, like imagining movement.
Motor imagery BCIs, right?
Yep. Then there's neuromarketing and emotion recognition. EEG
Yeah,
can
we're not
predict
doing
consumer
that.
choices or identify emotional states like valence with surprisingly high accuracy, sometimes over 97% with minimal sensors.
So you can actually gauge emotional responses directly from brain activity.
To a degree, yes. And monitoring critical brain states, think about assessing a pilot's alertness or drowsiness or tracking sedation depths during surgery. Advanced models using raw EEG are achieving very high accuracy there too, like 0.95 accuracy for sedation monitoring.
That's crucial for safety.
Absolutely.
Yeah.
And finally, understanding motor control. We analyze how alpha and beta brainwaves change, that's ERD and ERS in sensorimotor areas, to see how the brain prepares and executes movements.
It's incredible, really. The level of precision and insight we can get from these electrical signals using modern processing is just staggering.
It really is. These tools aren't just enhancing the data. They're fundamentally changing what we can learn from EEG. They're leading to better, more cost-effective diagnostics and opening up entirely new ways to interact with technology and understand ourselves.
So thinking about that, with these techniques getting ever more sophisticated, revealing this intricate dance of neurons, what new, truly personalized insights into our own minds, our own cognition and emotions might be waiting just around the corner for you to unlock?
This one seemed to be like ringing at time zero there. Not sure what's happening. But it's just double checking that it looks correctly. Yes, so I have EMG, very strong EMG that will just have an increased amplitude. Yep, so that's works okay. And then you have, those will be your eye blink signals, so they look like that. And now in theory you should have more of them. That doesn't seem to work as expected. Or is it just the amplitude? Oh, okay, it's the same kind of amount, like a random amount of eye blinks, 2 or 3, 1 or 3, but then at a different amplitude. Then you have your delta, theta. Yeah, that's overlaying them on top of one another. Yeah, so not sure what else we can add to this one. It mentioned the ICA, BCA, so independent component, principal component analysis. Yeah, so we have a different simulator for that. Could really use a better screen overlay. I mean, if I'm on a bigger screen, it will look better.